Let's go ahead and get started. You have found your way into the October edition of the University Lowbrow Astronomers Monthly Meeting. I'm Charlie Nielsen, the president of the club. It seems like it's been forever. Someday I'm going to get out of it. Anyway, we have a few other officers available, and we'll take some reports from them later on. But as tradition would have it, we always have our guest speaker first in the event that people wanted to just see the speaker and didn't want to stick around for a highly entertaining business meeting. And our speaker tonight is Dr. Greg Tarle, who is an emeritus professor of physics from the U of M, now living in paradise. Yes, he moved to Hawaii. In fact, when you see the picture a little bigger, I'll have you do that first before you go to that. Show them your background. It's rather nice. Anyway, yeah. He retired from, pardon me?
Should I stop sharing?
Yeah.
So you can see my background?
There you go.
Okay.
Looks pleasant, doesn't it? It's on the North Shore of Oahu, so. Anyway, he retired from active faculty status from the U of M in December 31st of 2022. Professor Tarle received his Bachelor of Science from the California Institute of Technology in 1972 and his PhD from the University of California, Berkeley in 1978. He joined the University of Michigan faculty as an assistant professor in 1984, was promoted to associate professor in 1988, and then professor in 1994. Greg has enjoyed a long and extraordinarily successful career that spanned the fields of experimental astrophysics and cosmology. Early in his career, he created experiments that flew on balloons or resided in deep underground laboratories to study the antimatter content of cosmic rays and search for magnetic monopoles. These efforts established Professor Tarle as a leader in experimental high-energy astrophysics and consequently named a Fellow of the American Physical Society, and that happened in 1997. More recently, Professor Tarle became a major contributor to two of the world's most impactful cosmological experiments. Tonight, he is here reaching across half of the Pacific Ocean to talk to us about his most recent work, which is a theory about how cosmologically coupled black holes could be the origin of dark energy. Pretty enticing, if you ask me. So, with that, let's learn about it. I'd like to introduce Professor Greg Tarle.
Hello, everyone. It's nice to be here with you. Well, nice to talk to all of you. The weather is probably really nice there.
No, you can.
Oh.
Ask to unmute. Click that.
There, can you hear me now?
So, here you go. But make it.
I got it.
Okay, well, it's very nice to be here with you and talk to you about this wild new theory on cosmologically coupled black holes. It's going to be more than that. I'm going to talk about a scientific adventure that I began, a little over 25 years ago, when I got involved in experiments to look at, try to figure out what the origin of dark energy is. So, to take you back to 1998, I was giving a talk at a conference it was called the UCLA conference on dark matter. And I have been doing balloon experiments in which I had seen that the positron fraction had begun to rise up, and this was possibly indication of a dark matter origin of this. But I was sitting in the audience at this conference, and my old friend Saul Perlmutter, who I knew from Berkeley, he was a graduate student at the time when I was a research scientist, was giving a wonderful talk about this exciting new result. And there were the competitors giving their talk, and there was a lot of argument back and forth. And this whole idea of dark energy came to be at that time. And I at that time, I said, wow, this is really interesting. And I kind of switched fields, something that everybody should do every once in a while. I decided to work on this problem. So anyway, oh, it's not advancing. Just a second. Oh, there we go. And so what happened then in 1998 was the start of a revolution in cosmology. The supernova cosmology project that Saul was leading and the High Z supernova team used these type 1a supernova as standard candles to construct a Hubble diagram out to a redshift of about 1. They all expected that they would observe the slowing down of the expansion, the deceleration of the expansion, because of the matter content of the universe. And they figured they could measure the matter content of the universe and figure out whether we were a closed universe or not. But contrary to expectations, both of these experiments found that the expansion of the universe is accelerating. So the stuff responsible for this acceleration was given the name dark energy by Michael Turner sometime after this. But I found this magic card from 1996. I don't know if I can blow it up. Can you see that?
Yeah.
Anyway, it has a copyright of 1996 by Kazuki Takahashi, and it says that if you have this magic card, a fiend-type monster equipped with this card increases its attack and defense by 300 points, which makes dark energy very powerful. So Mike Turner may have independently come up with the name dark energy, but it was in existence before this and a long time before this. So in 2011, Saul Perlmutter in the upper right and Brian Schmidt and Adam Rees were awarded the Nobel Prize in Physics for discovering the accelerating universe. And as I said, this was an absolute revolution in cosmology because it basically said, and if you look at this graph here, this is, on this scale is the fraction of the critical density made up of this new stuff, this dark energy. And here is the fraction of the critical density made up of matter. And on this plot, you see the supernova data from that time was showing that that this stuff is not zero, that there is some of this stuff present. And depending upon what omega matter actually is, it could be anywhere along this line. And but at the time, there was a mass census that had been done using clusters, and it was telling us that there was about 30% or 30%, 25% matter in the universe, which consisted mostly of dark matter. But that was what the clustering told us, that it was about there. And so by combining these two results, it would say that the amount of dark energy was about 70% of the critical density, and the amount of matter was about 30%, as indicated by these clusters. But then came along the ripples in the cosmic microwave background measurements, and the cosmic microwave background, from looking at the first acoustic peak, it's telling you the curvature of the universe. And so the light either, sort of converges as it goes towards you, in which case it would look, these structures would appear larger, or it comes to like a concave space where the structures would appear smaller. And but they didn't appear larger or smaller than they should have. They were, as Goldilocks said, just right. And that told you that the universe was very flat. And the flat universe lies along this line where omega lambda plus omega matter, if there was nothing else, if there was no curvature, would be along this line. It would be equal to 1. It would basically close the universe not close to the universe, it would flatten the universe. And it would lie along this line. And the supernova is pretty orthogonal to that, because that's measuring the competition between this dark energy trying to fling the universe apart and this matter that's trying to pull it together. And so you're seeing omega lambda minus omega matter lying along this line here. You make a measurement of that. So anyway, you could take any two of these things and of these measurements, if you don't believe one of them, and they would agree that there's stuff in the universe that we had previously not thought about, this dark energy, at about 75%, 75%. And the matter makes up about 25%. And so there is what emerged was a standard model for cosmology, where 75% is dark energy, 25% is matter. Only 0.5% of the stars that we look at when we look out through telescopes, and and then of this 25% matter, you got 20% of the universe is made of dark matter. 4.4% of the energy in the universe is made of baryons, the stuff that you and I are made of, neutrons and protons and stuff like that. And 0.3% are made of neutrinos. And so this is very nice. We have this nice standard model, but it's very unsatisfying because, we don't understand 96% of the universe. We don't know what the dark matter is to this day. And we have very little idea of what the dark energy could be. And so, you could say, well, that's really bad. We, only know what 4% of the universe is made of, but it's actually a good thing, because it means that there's work to be done, that we can try to figure this out. Now, so the picture that emerged of the evolution of the universe was that off to the left over here, can you see my cursor?
Yeah.
Okay.
Yeah.
So off to the left over here, the universe began in some inflationary period, where there were quantum fluctuations that in the early universe that led to this inflationary period where the universe expanded superluminally. And in something like 10 to the minus 32 seconds, it increased its size by an enormous amount, and therefore flattened the universe. The fact that you can see off in one direction, the microwave background at a certain temperature, and then you can look over in the other direction and see it at the same temperature, meant that those two things that are separated today by twice the Hubble scale had to be in communication at some early point. And the only way that could happen is if there was some period where the universe inflated. Now, this doesn't mean that anything is moving faster than the speed of light. It's just that space-time is expanding faster, so that there's a horizon, and it looks like things that are far away are actually, over the horizon and moving away from us at faster and faster speeds. But it doesn't mean that just because the universe is expanding so-called superluminally, it doesn't mean that things are moving faster than the speed of light through space. But anyway, that's the idea, that there was this period of inflation to explain the uniformity of the microwave background radiation in all directions. And then something happened. Whatever was the cause of this thing, something happened to cause this inflation to stop. And then what happened is it turned into the matter and the radiation, and then ultimately the matter that makes up our universe today. And so the universe continued to expand, and it continued to cool. And when the temperature got below about 3,000 Kelvin, atoms could form. Before that, it was just a plasma in the early universe. But at that point, atoms could form. And then there was a burst of ultraviolet light that was released. And, just like when you look at a gas discharge tube, it looks opaque when it's a plasma, when it's there are ions, and as soon as you turn it off, it's transparent. And so that's what happened to the universe. This ultraviolet light, this burst of ultraviolet light that was emitted from the material at that time when they formed atoms, just free streamed throughout space, and it was it didn't interact anymore very much, and so it just it's been streaming through the universe ever since, and as the universe expanded, that light stretched. And today, that light that was emitted in the ultraviolet is at about 380,000 years after the launch of the universe, is now seen in the microwaves, in the microwave regions, because it's stretched. Then followed a period where there was this dark ages where there wasn't much going on. Well, maybe there was with the dark matter, but you couldn't see much. And then stars began to form at about 400 million years after the launch of the universe. The stars that we know and love as astronomers. And then star formation began to peak, and then star formation began to kind of die off. But then, just about the time when star formation was kind of peaking over here, and galaxies and the galaxies and planets were forming, and us, we started to undergo a period of acceleration again. That's what this dark energy is telling us. And, it's starting to accelerate the universe, very similar, except maybe less so than the inflationary period, at the beginning of the universe. And so here we sit at 13.7 billion years after the launch of the universe, and the universe is doing this again. It's starting to accelerate in its expansion. So what could cause the expansion of the universe, the Hubble expansion, to accelerate? Well, if you take Einstein's field equations of general relativity and apply it to the whole universe, as Friedman did, and you add the fluid equation, you get a thing called the acceleration equation. I'm not expecting you to follow the mathematics here unless you've taken general relativity, but what I want you to look at over here is this equation over here and this negative sign here. Now, what this equation is telling us is what the scale factor is doing. And the dots above the A over here indicate the change with respect to time. And the two dots means the change in the change with respect to time. Okay, so it's an acceleration of the scale of the universe. The scale factor is given by 1 plus 1 over 1 plus the redshift. At the current redshift of 0, redshift is delta lambda over lambda, this amount of stretching. The scale factor today is 1. Okay, so it's all relative to today's scale of the universe. And so at the beginning of the universe, the A was 0, and now it's 1. And so if you look at this equation, what Einstein's equations are telling us, as written down by Friedman, is that if the density, which has to be positive, this is the density of all matter and radiation and everything else that's in the universe, including dark energy, anything, if that's positive, and pressure typically is 0 for matter, but this is pressures as we know it now is you think of it as positive, that the universe should be decelerating under the presence of the matter in the universe, but it's accelerating now, and that's how do you get that to happen? Well, these are just constants. This is the gravitational constant. This is the speed of light. And then you have this rho plus 3p. So how do you make the sign change from negative to positive? And the way you can do that is if you have what's known as negative pressure. And if the pressure is much less than 0 and it's large, this term rho plus 3p can be negative. In other words, if p is less than minus 1/3, then this can switch from negative to positive, this sign here, and the universe can be accelerating. Okay, so negative pressure, that's a weird idea. And so the question is, what could be providing such negative pressure? Well, Einstein originally, when he wrote down his field equations, he saw that Friedman, he wrote down his field equations. They were, just based on the equivalence principle. And then when Friedman showed that the universe either had to be expanding or contracting, it couldn't be static, Einstein said, "Oh my goodness," matter would pull it together. Einstein said, "Oh my goodness, I I made a mistake. That is my biggest blunder," he said. He said that he added in this cosmological constant, which he called lambda. And it has an equation of state. If you put it on the right-hand side of the Einstein equations, which is the equation of state is the ratio of the pressure to the density. And this type of cosmological constant would have an equation of state of -1. It's called vacuum energy. In other words, energy that's associated with the vacuum, with empty space. If you take everything out of empty space, and take everything out of space, and what is left with is some energy left over, and it turns out it's not small compared to its density. And so he called it his biggest blunder. But was it his biggest blunder? Because now we see the universe is accelerating again. And if you have a p over rho, which is, anywhere between -1/3 and -1, you can actually get the universe to accelerate. So it could be Einstein's cosmological constant called lambda. The other possibility is you can come up with a new field, a new particle, and say, okay, it might be a particle that has time-varying equation of state. And the simplest form is called WOA, which we use to figure out whether the equation of state is changing or not. If it's not changing, then we'd find that this WA would be 0, and there would be no dependence on the scale factor of the universe, and it would always be this value W naught, a constant. And but if you find that this term over here, WA, has some value to it, well, then it will have some evolution with the universe, and the equation of state would be changing. And so that, is one way you can look for this dark energy, the effect of the dark energy, and figure out what it is. So the other possibility is that gravity is just plain wrong. Einstein was wrong. And the way to measure that is by measuring the growth of structure versus the growth of the universe. And then the other possibility is something we just haven't thought of yet, something completely new. Okay. So, that's how things stood 25 years ago. In fact, they've stood that way for most of the 25 years following the discovery of the accelerating universe. But I was still very confused at the time when I started out in this field about what this negative pressure, how this negative pressure works. And so what do you do when you don't understand something? What you do is you go to someone who is very wise, very knowledgeable, and can give you very good advice, right? And so I went to see my old wrestling coach, Dave Schramm. He was also a cosmologist, but he was also an NCAA champion. Anyway, this is what he told me. So I'll tell you what he told me. He said, with an ordinary gas of particles, as you increase the volume of the box of holding these particles, the particles will dilute. And in doing so, because the pressure is positive for a gas of particles, it does positive pressure volume work, expanding the box, and the energy content of the gas has to then decrease. Now, what is this called? I'm asking you. What is this called? Everyone has one of these in their house. Can someone tell me?
Air conditioner.
Yeah, or a refrigerator, right? It's a refrigerator. That's how a refrigerator works. You take a volume of gas, you expand it suddenly, and you just let it through a valve and expand it, and the pressure is greater than 0, the density is greater than 0, the equation of state is greater than 0, and you can get cooling. Okay? Now, what if you have energy that's associated with empty space? We call it vacuum energy. So because it's a property of empty space, as you increase the volume of the box, you got to get more of it, right? Because its density is constant. Okay. So, because it's just a property of space. It has a certain constant density. So the energy content of the box has to increase. But how do you get the energy content of the box to increase? Well, the vacuum energy pressure has to be negative, so that the negative pressure volume work is done expanding the box, and the total vacuum energy in the box increases. Okay, what is this called?
Backup compressor.
No. It's called a space heater. That's my one dark energy joke. I'm sorry if you didn't like it. Okay. So in the case of vacuum energy, the pressure is less than zero, the density is greater than zero, and in other words, the energy density is greater than zero. It's going to be gravitationally attractive because of that, but the pressure is less than zero, so the acceleration is gonna cause it to be kind of repulsive in terms of space. Space is going to expand and accelerate out, get larger. And the equation of state is less than zero. The equation of state, pressure over density, is less than zero. And so that's how you look for this thing. You try to measure the equation of state and see if it's, see what's happening to it. So how do you understand the nature of dark energy? Remember, at this point, the theorists were totally stumped. They could not figure out what was going on, what was causing this accelerated expansion. And so solving the mystery of dark energy required new observations. And the strategy was to measure the equation of state as a function of redshift. And also, if you wanted to know whether it was due to gravity, what you could do is you could measure the growth of the scale factor versus the growth of structure. So the big question that needed to be answered experimentally, and it's now in the hands of the experimentalists like me, does dark energy vary in time? Is it a cosmological constant or is it not? Okay. And so there was a dark energy task force put together 8 years after the discovery of the accelerating universe in May of 2006. Rocky Cobb from Chicago was the person leading that group. And they identified 4 observational techniques that could be used to make these measurements. One was galaxy clusters. The other was supernova, like had been done. There was weak lensing. And then there was baryon acoustic oscillations. I'm going to describe to you what that means later. So they came up with a figure of merit for new experiments. And it was, get this, the reciprocal of the area enclosing 95%, the 95% confidence limit in the W0 WA plane using this equation, this WOA equation, this very simplest linear model, that W0 plus WA times 1 minus A is the parameterization that describes dark energy. Okay. It's a very simple model, but it doesn't have, they say it's motivated by physical theories. I don't believe it. It's just, it's just a parameterization. Okay. And so the idea was that you could judge the value of an experiment by determining this figure of merit for that experiment. How well could you measure W0 and WA? So they proposed a 4-stage program. There was a lot of money involved, by the way. And so stage 1 was what was already known, from all the experiments that had been done. That had been done. Stage 2 was what was anticipated with projects ongoing at that time. And of course, they're over now. Stage 3 was to develop near-term medium cost experiments, medium cost existing proposals that provided an increase in the figure of merit by a factor of 3 over what was going on with stage 2 projects at the time. So one of those proposals was to produce the so-called dark energy DES, which is the dark energy is a dark energy instrument. So anyway, I actually worked on that for many years, and then they proposed that beyond that. By the way, DES is a imaging instrument. They proposed that for stage 4, you had to produce a figure of merit increase of a factor of 10 over stage 2, and those. Oh, by the way, DES is finished now. It was a 5.5-year survey. It's complete. Analysis continues. But then the idea was to produce these stage 4 long-term missions, which produces this increase in the figure of merit. And this was DESI. And I'm a big part of DESI, I think. And so the data release 1, which was the year 1 of data, has already been done. That was done about a year and a half ago. And then DR2 was 3 years of data of a 5-year survey. And that was released about a year ago. Oh, actually, it was released, sorry, it was released in March of this year, half a year ago. And then of the 5 years, we've already collected 4.5 years of that data, actually a bit more. And there's an extension that's been approved for another 2.5 years until the end of 2028. And then it's going to happen. DOE is actually going to fund us to do this. DESI 2 is going to start in January of 2029. It's already on their books. And then there's a much larger experiment called SPEC-S5 on the horizon that would be done maybe in another 10 years. So anyway, that's the experimental landscape. And so let me tell you about the dark energy spectroscopic instrument. This is the first stage 4 experiment on the sky. It's located, we basically commandeered the entire male 4-meter telescope at Kitt Peak to do this experiment. And what we did is to build a new camera over here. And at the front of the camera is a 6-lens wide field corrector, which takes, the tiny, keyhole in the sky that the male looked at, and it expands it into something several times the size of the moon, several square degrees. And then at the back, there are 5,000 fiber positioning robots, which are over here. And I put the big M here because they were built at Michigan. I was in charge of this project of building the robots that position fibers on galaxies that are identified through imaging surveys, that we did before DESI ever got started. And then there's a 49-meter 5,000 fiber run from all 5,000 robots that goes down the arms of the telescope, down to the Coude room, where there are 10 3-band 500-channel optical near-infrared spectrographs, medium resolution, and you can see the picture of them over here to the left. And then there's a fiber view camera in the right in front of the hole in the mirror that looks up through this optics here to the focal plane where these fibers are. They're backlit, and you can tell where they've gone to, and it provides feedback for fine positioning of these. And the positioning of these robots is accurate to 5 microns. And so you can place the point spread function of a galaxy, right in the middle of that to very high accuracy. The point spread function is about 85 microns. It's 109 micron fiber, and you can place it to an accuracy of 5 microns. So that's what those robots do, and that's how DESI works. So I'm going to play this video for you, which talks about how DESI was put together, because it's really an exciting kind of project. It's kind of, as Joe Silber, who is the chief engineer of this, says, is a crazy machine.
The DESI project is a crazy machine. It's really exciting to work on. It has 5,000 individual fiber positioning robots. Each one moves a single fiber to target a single galaxy at a time. And that allows us to do massively parallel survey of the universe, where we can measure 5,000 galaxies at a time, very precisely measure their light, take spectra, and then move on to the next set of 5,000 every 20 minutes. So it's a rapidly cycling survey. Here we're installing the fiber positioner robots into the petals. There are 10 petals. Each one of them is a 36-degree wedge, and 10 of those form the focal plane of the DESI instrument. Each petal has 500 robots, and each robot has a single 3-meter length of fiber. Those fibers then need to get spliced to a 50-meter cable. Each cable carries 500 fibers, and those ultimately route down off the telescope to the ground floor of the telescope, where they're the spectroscopes that measure the light. Every fiber positioner has been built at the University of Michigan, mostly by undergraduate students in physics and mechanical engineering. There's over 20 parts in each robot. In fact, the DESI focal plane has over 600,000 different parts in the DESI focal plane, which is only a volume about this big. As I said, it's a crazy, insane instrument that we're putting together. Once the fiber positioner robots are built, they're sent to Berkeley, where we have acceptance testing to make sure that every positioner works as expected. And then at that point, we install 3-meter lengths of fiber in each positioner. In this room, we have 3 different clean hoods. And under each clean hood, we do the assembly of the petals, and we do the splicing of the fibers to the long fiber cables.
We fuse the fibers because we build the front end focal plane system in one section, and then we build the fiber cable to the spectrograph split assembly in a separate section. And then we have to join those two sections together. The most efficient way to do that is with fusion splicing. So we expose the bare strands of glass, and then we heat them up in a very precise way to make that connection without any losses in terms of optical quality or throughput or any degradation of the light.
And all this is done under fairly clean conditions. There's laminar clean flow of air coming down on top of all of our assembly areas to keep out the dust and contamination. My favorite part about this project has been packaging the focal plane. And I'm talking about making all of these 600,000 different parts all fit together and be assemblable. And it's been amazing after having done literally years of modeling in the computer, how all these parts were going to fit together and work together, to see us starting to put the real hardware together, and it actually just fits. That's really gratifying.
Okay. Well, anyway, that shows you how DESI was put together. This animation shows a 3D model of DESI's focal plane. The movement of the 5,000 robotic positioners is coordinated so they don't bump into each other. Computer programs prevent collisions. And they overlap. They have overlapping control disks.
They can hit each other if you weren't careful. I was visiting KP, taking it, put that, I didn't know that this was between 2 years. That's how it's just awesome. I remember now they talked about that, about Desi. Yeah. Spectrum. It's interesting.
So DESI started a 5-year survey in 2021. The 5-year survey is almost done. This shows you a slice of the 16 million galaxies that have had their spectrum measured that came from the 3 years of data. And so this is, as you can see it's easy to, in this blow up, to see the structure of the underlying structure of the matter in our universe. This is just a thin slice of the full map so that you can see this. And so that's really what DESI did. It's really cosmic cartography. We've measured the 3-dimensional positions of galaxies out there. And so what we do is we use that to study the evolution of dark energy over cosmic time. Nothing would be complete without a fly-through of the DESI galaxy map, so I'm going to show you that. So the idea between producing this map is to measure the competition between dark energy trying to fling the universe apart and to measure the matter trying to pull it together. And you do this as a function of redshift. It's 3-dimensional rather than, say, the microwave background radiation is, which is 1-dimensional. Sorry, 2-dimensional. Anyway, that video was made by the Fisk Planetarium in Boulder. So let me tell you about the technique that was used by DESI. It's a very nice technique. It's called baryon acoustic oscillations. So the idea is that if you have a plasma, in other words, ionized gas, like you have in a, when the temperature is above 3,000 Kelvin in the early universe, well, sound waves will propagate at roughly the speed of light over the square root of 3 in a plasma. And so they propagate outward. Every little hiccup that happened in the very early universe, due to these quantum fluctuations, will propagate outward until there's no plasma anymore, until the temperature drops below 3,000 Kelvin, When atoms form, sound stops at that point, and UV light is free to stream out. And then the light gets stretched into the microwave radiation at the present time today. And so this is, on the left, you see the universe at 380,000 years old. That's the cosmic microwave background radiation at the surface of last scattering. And then you have the universe today in the galaxy map. And what happens is the dense regions in this microwave background map, fluctuation map, they're going to grow gravitationally, and the sparse regions are going to become more sparse. The rich get richer, the poor get poorer, and you end up with this foamy-like structure like this. And what you're doing is you're following the horizon, the sound horizon, from 380,000 years ago to the present time, and also at intermediate redshifts. You can watch this standard ruler, the baryon acoustic oscillations. That's going to be the dominant scale on the sky, and you can watch it grow over cosmic time. And that's how we do this. Okay, so this is the origin of the 1 degree angular scale acoustic peak in the cosmic microwave background radiation that you see here. And that 1 degree is going to grow into the structure that we see today. And so, just a second. So these fluctuations are 1 part in 10 to the 5, 1 part in 100,000, which gravitationally grow into these structures that we see today, the so-called baryon acoustic oscillation feature. And those are, unity scale fluctuations where you have voids and dense regions. And so this is what DESI sees. There are a number of tracers. There's bright galaxies, bright galaxy survey. There's luminous red galaxies. There's 2 of those points there. There's luminous red galaxies and emission line galaxies at higher redshift. There's emission line galaxies, more of them. And then there's quasars and Lyman alpha. As you can see, we can measure the size of this baryon acoustic oscillation peak, and we can do it very accurately. And we can do that as a function of redshift and watch how the universe has grown and compare it to what we expect from lambda CDM, which is the straight line here in the middle. And you can see that there are deviations from that. And when you apply the WOA model, you get a better fit, significantly better fit. And the question is, can you rule out lambda CDM? So the way you try to rule out lambda CDM, oh, by the way, Claire Lamont made this really nice little sort of annotated figure, the same figure, and you can see what all these things mean if what I just said doesn't make too much sense to you. You can go on the web and you can see Claire's annotated plot of this graph, and basically she called it tracing the expanding universe with bubbles. Those are the BAO bubbles, and for the different types of tracers as a function of redshift. And so she relabeled the axes and relabeled the scale down here. So I'll send you there if you want to see this. It's kind of cute. Anyway, so this is how DESI makes its measurements. We get spectra of tens of millions of galaxies. In the 5 years, we'll have something like 40 million galaxies, which is about 20 times what previously had been done by all spectroscopic measurements to date. And in the extension, we're going to add to that. So we're going to probably reach around 50 million, 55 million, something like that, galaxies. It's an enormous number of galaxies, and you can use that a lot to beat down your statistical errors. One of the nice things about baryon acoustic oscillations is it has a very small systematic error, roughly at the few percent level. And so we got plenty of room to keep using this technique without worrying about systematic errors. Anyway, you can see the spectra that's been taken. Here's an example of a quasar. You can see the oops. What happened? You can see the spectra that's been taken, and from that we can determine the redshift. This particular quasar was at 1.2 redshift of 1.24. It's one of our more distant things. There are emission line galaxies at lower redshift. Those are in blue here in this picture here. And you can see where you can see the oxygen doublet and the O2 line. And so we can measure the redshift there. This turned out to be a redshift of 1.14. There are luminous hello? Questions? Okay. There are luminous red galaxies. Here's a luminous red galaxy with, you can look at the spectra for that. You can see the lines. The redshift here is 0.82 at lower redshift. And then there's a bright galaxy survey at the lower redshifts. So it covers a wide range of redshifts. And you can see the baryon acoustic oscillation feature grow and change as time goes on.
So question is, from the data that you get from the spectra, can you see any chemical differences between all these?
Oh,
different-
yes. There's a lot of stuff that DESI does that has nothing to do with dark energy. And there's a whole group that does this.
Because
It works.
you're identifying specific spectral lines that identify elements, and using that, you can then calculate what the Z is, the redshift, by like the oxygen, ionized oxygen, the O3.
Oh yeah, and there's plenty of people in DESI who are very interested in this and are following up on, you know, the evolution, the chemical evolution of these galaxies.
So for every one of those galaxies, you got a full spectrum, a full chemical spectrum.
Absolutely. Absolutely. It's
That's
amazing.
an enormous amount of data. Wow.
And you know, the data is made public, so you can go look at it. You know, after a year of us focusing on it and, you know, coming out with the main results, it's made public and it's available to everybody. And so it's an enormous data set. It's an amazing data set. Anyone can look at it. So anyway, here's what we found. And I have to tell you that when we first saw this plot, it was in Hawaii. I had organized a meeting of the DESI collaboration in Hawaii, and that was going to be the reveal of the data. When we first saw the DR1 plot of this, the way we did it is by blinding the data, and then we unblinded it. So even the person presenting the data didn't know what was going to happen. We unblinded it during the coffee break, and then it populated the slides of the speaker, and everyone was watching this, and we're just our mouths kind of fell open because we were so surprised. I among others expected what would happen, you know, was that we would measure something very close to W naught equal -1, with WA very close to 0, if not 0. And we'd find lambda CDM, and that was it. And, you know, where do you go from there? Okay. But what we found was totally surprising to everybody. We unblinded the data and then published what we unblinded. We did not do further, you know, processing of the data. And so when we looked at the data, we found that not only was W naught not equal to -1, but there was a significant value for WA. And this is DESI DR2, by the way. And as you can see, we have to compare, you're adding DESI plus the cosmic microwave background data as a you know, signpost. And then, you know, because really that's a BAO feature at a redshift of, you know, 1100. And then we had to add to that, if you have no supernova, it gives you these fairly large error curves, although it does deviate from here. It's not by many sigma, but we have to add the supernova data, and there's 3 of them: Pantheon, Union 3, and DES year 5, the Dark Energy Survey year 5. And as you can see, as you add these data sets, you get to 4.2 sigma separation from W naught equal -1 and WA equals 0. Now, it's not 5 sigma, which is the gold standard for making a discovery, although, you know, 4.2 sigma is it's incredibly unlikely that it's just a fluctuation. So anyway, for the dark energy equation of state, we use the WOA value for the equation of state, the parameterization, and then we fit those values. We extracted those values, And we were able to reject lambda CDM at 4.2 sigma using the Dark Energy Survey supernova data set. The conclusion was that dark energy was evolving. It's not a cosmological constant as everyone had imagined it would be. And when you write down, you can actually write down in closed form based on the values we get of W naught and WA, how the dark energy density varies with redshift. And it's just given by this equation. You can plug in the values for W naught and WA from this graph, and you can draw a function of how the dark energy density is varying with redshift. And this is the equation. But WOA has what I would call issues. There's several things. One is that there is a so-called phantom crossing. W goes less than -1 for redshifts greater than this value. Okay. Now, if W becomes less than -1, remember this is a ratio of pressure to density. It means that the sound speed is greater than the speed of light. That means that it violates causality. Okay. And the only way to get around that, theoretically, is if you're creating dark energy from another species, that there's something going on like that. But we got that in certain regions of redshift space, W is less than -1, and that just it's not physical. So that's one of the problems with WOA. So my feeling is that WOA is very good at determining whether or not dark energy is changing, but it doesn't necessarily tell you how it's changing. So anyway, it also doesn't allow for asymptotic behavior. In other words, does the dark energy density start at some value, low value, and end up asymptoting at some high value, or does it start at some high value and go away? Okay, but this equation here, up here, this rho dark energy, must have a peak when you analyze things with WOA. It has to have, this has a peak. It's mathematically has a peak. So in other words, if you see the dark energy rising up at high redshift, it has to come down if you're analyzing things with WOA. And this has been, I should say, misinterpreted by some of my own colleagues on DESI. And so the question is, okay, so you found out that dark energy is changing. How is it changing now? And the answer, the proper answer is within the WOA parameterization, it is thawing now, it's declining, okay? But in the past, it rose up to some value. And as I said, this is just an artifact of the WOA model. The incorrect answer is it's declining now, because we don't know that with high certainty. We just don't know that. So anyway, it has to peak, but it also doesn't model possible interconversion, as I mentioned before, of dark energy with another species. In other words, matter turning into dark energy. That would fix the phantom crossing and make it physical. And that's where what I'm thinking now. So anyway, I want to tell you now about this unconventional idea for the origin of dark energy. So I'm going to back up about 7 years. And I had just, it was 2018, and after I delivered the fiber positioner system for DESI to Lawrence Berkeley Lab, several years before DESI would take any data, I decided to take a well-deserved 15-month sabbatical at the University of Hawaii in Manoa. And when I took that sabbatical, I was at the Institute for Astronomy, and then I would go down a couple days a week to the physics department. They're separate. And so physics department, my first day in the physics and astronomy department, I was approached by this young theorist, Kevin Croker, who handed me, he came into my office, he was really enthusiastic. He handed me drafts of papers he had written, including his thesis. And he asked me whether DESI could see this effect. And, you know, uh, I looked at these papers and they were full of general relativity calculations, way beyond what I had learned 44 years before in graduate school. But he was so enthusiastic, I didn't have the heart to turn him down and say, I can't go through all this stuff. And after all, I was on sabbatical. So I decided, okay, I'm going to actually try to understand this stuff. He just was so enthusiastic. Anyway, I had to relearn my general relativity and then some. And it took me 5 full passes to go through these papers and reproduce the equations to understand them. And I'm not a big computer algebra person, so I had to do it by hand. Anyway, I was doubtful that the effect would be large enough when I finally got through it for DESI to see, because I thought that W naught was going to be really close to 1 and WA was going to be really small. But I couldn't find anything wrong with the calculations. I actually sent it to a theorist in the physics department at Michigan and asked him what he thought about it. And he took a month, longer than I took, and he went through the calculations and he said, I can't find anything wrong with it. And so at that point, the idea behind these calculations was that there are what are called non-singular black holes that don't form a singularity at the center. Einstein never believed in singularities, even though his equations predicted them when they predicted black holes. And the idea was that these non-singular black holes could contain energized vacuum or vacuum energy, originally proposed by someone called Ernst Leiner. Anyway, that it would couple to the external cosmology and could contribute to the late time accelerated expansion. And so Kevin had done this work with a mathematician at the University of Hawaii. He was a geometer, Joel Weiner. And so I was sufficiently intrigued by all this, that it might explain the dark energy, that I joined a kind of small ragtag group of scientists to explore the possible observational signatures of these cosmologically coupled black holes. And the paper that was handed to me that I had to read, that I read, eventually appeared the following year in the Astrophysical Journal. And if any of you want to see what I saw and had to read through, it's pretty heavy duty GR. But here it is: implication of symmetry and pressure in Friedmann cosmology, 1 formalism. So there was going to be a 2, obviously. But it appeared in the Astrophysical Journal. And I think if you read it, you'd find it as incomprehensible as I did. So anyway, let me tell you about these cosmologically coupled black holes, because they're kind of interesting. And the idea might be wrong, but it's gained a certain amount of acceptance in recent years because the evidence for it keeps mounting. So let me show you what they are. So for the last 27 years, the conventional wisdom among theorists, as I told you, was that dark energy arises from quantum fluctuations in the vacuum. In other words, every cubic Planck-Compton wavelength of space has a virtual Planck mass particle in it that lasts only for a Planck time and then has to pay back the Heisenberg's uncertainty principle. And it's filled with this stuff, all these virtual particles. It's the basis behind quantum field theory. Anyway, if you do this, you find out that you get a dark energy density, which is 120 orders of magnitude, 10 to the 120 times too big, larger than 120 orders of magnitude higher than has been measured. Okay, but what the theorists would say is, well, maybe there's some cancellation that takes place, like it happens in lots of quantum field theories. There's cancellations that take place because to get rid of the infinities. Okay, that's possible. But why would something cancel to 120 orders of magnitude and not cancel to 0? What does that, right? And so there was a lot of problems with this whole idea that quantum fluctuations in the vacuum lead to the cosmological constant, because it doesn't. It leads to something too big. So there are other problems besides this, what's called the cosmological constant problem. There's a coincidence problem, which is why now? What's so special about now that we see the dark energy dominating over matter? Why? And then there's the new cosmological constant problem, which, kind of shoves the old cosmological constant problem off by 120 orders of magnitude under the rug and says, why is the dark energy density comparable to the matter density? How could that possibly be? What's connecting the two? Well, it's giving you a clue. The universe is giving you a clue. So anyway, given these and the fact that DESI now found that dark energy is evolving, maybe it's time to explore some new ideas from the old idea that it arises from, it's a property of the vacuum and is distributed through all of space. So in the very early universe, we underwent this period of rapid exponential expansion called inflation. And presumably that was driven by some sort of vacuum energy that caused A double dot over A to be positive. Of course, we don't understand the physics because, it's the densities and pressures and everything is so large, and the curvature of the universe is so large, actually so small, it's one over the curvature. Anyway, is so great that the curvature is so great that in the early universe that we just don't understand the physics there. We can't reproduce that with the accelerators on Earth. And so we know that this inflation existed because the universe is so flat, there are no monopoles, and there's other reasons why why inflation has to work. There's other indications that inflation is right. It was invented by Alan Guth at MIT. But whatever the cause, this inflation stopped, and the inflationary vacuum energy turned into the matter of our universe. Now, in the late universe, the universe is doing it again. It's accelerating again, and we call it dark energy, but, it may be related to this early universe expansion and this inflation. So I'm going to ask you a question. Where in our universe do such extreme conditions, the density, the temperature, the gravitational fields, the curvature, such as those that existed during inflation, where do they exist today?
Black holes.
Black holes. When you have that's the answer, at the center of a collapsing black hole, you have these enormous, it's the only place that you have these enormous densities, temperatures, pressures, gravitational fields, curvature. That's the only place where you can mimic this place in the universe, at the beginning of the universe, where some sort of vacuum energy turned into matter. And so you might imagine that at the center of a collapsing black hole, everything's like run in reverse, like little big bangs played in reverse, where you're squashing the matter in there, getting it to very high density, and somehow it turns back into some sort of vacuum energy. Okay, this idea is not new. It's not new. It actually has a long history, and it didn't originate. The idea that you can form this energized vacuum didn't originate with Kevin and Klein and Weiner. So the question is it possible that black holes are the source of dark energy? And those of you who took general relativity in graduate school or undergraduate school now, we forget that when we did these solutions, these nice Schwarzschild and Kerr solutions, we forget that we assumed that the universe was flat and static, the external universe, and we matched them up, the boundary conditions, and we got these nice Schwarzschild and Kerr solutions. But we forget that these paper solutions are not the actual objects that inhabit our universe that we see out there. There's several problems with them. They don't match the expanding universe boundary conditions at spatial and temporal infinity that we know exist in our universe. The universe is expanding. You cannot match, you're not matching those boundary conditions in the universe in which we live. They contain these singularities, in other words, where matter is squashed to a point, which even Einstein knew that this was where his theory failed. That you don't have singularities. There's no such thing in nature. Something has to stop that collapse. Anyway, they also have these absolute static horizons. Everyone's heard in a black hole, what goes in never comes out, blah, 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 blah. But it's been shown that in any metric theory, that's incompatible with a dynamic universe, a universe that's expanding or changing. You cannot have a static horizon. The horizons have to change with the expansion of the universe. You can show that mathematically, and it has been done. So people forget that these black holes that they know and love are not the black holes that exist out there. Now, as I said, non-singular black holes with pressure equal to minus rho have a long history, starting with Kleiner in 1966. he's the one who said that, gee, at the center of a collapsing star, you might be able to generate this this vacuum. He said this vacuum energy. He called it the mu vacuum or the energized vacuum. He speculated that that might happen in a footnote, by the way, to a paper. And Sakharov picked up on that footnote and basically promoted Gleiner's idea. Anyway, Bardeen and Dimnikova followed through on this, mostly, a lot of Russian theorists who were ignored during that time. Anyway, one of the things that these non-singular black holes have is dynamical mass. In other words, mass that changes over time. And also the radius has to change, the Schwarzschild radius. So it's not an absolute static horizon. They'll mimic Schwarzschild and Kerr solutions on the outside for times much less than a Hubble time. But when you get to things, when you're measuring things over a Hubble time, they're not, unlike Schwarzschild and Kerr, they're coupled to the external cosmology. In other words, you can think of it as a rubber band. As the universe expands, they expand with the universe. And that means the mass has to grow. So could cosmologically coupled black holes, CCBH as we call them, be the origin of our late-time dark energy? Okay, so here's a three-legged stool. Everyone knows that you need to have a three-legged stool to be stable, right? You have one leg, falls over. Two legs, falls over. Three legs, that can work, right? So the Big Bang Theory, let me go back to the Big Bang Theory, didn't gain acceptance until there were three independent observations, or three legs supporting it. There was the Hubble expansion. There was but people still didn't, they thought that somehow matter was being created spontaneously as the universe expanded, the so-called steady state theory. The cosmic microwave background radiation temperature was measured at 3 degrees because this free streaming ultraviolet light expanded by a factor of 1100 since the microwave, since recombination, when the microwave background radiation was released. And it got released in the ultraviolet, and it has since stretched to a temperature of 3 Kelvin, as predicted by the redshift of that period. Anyway, then it still wasn't accepted. And then there was Big Bang nucleosynthesis, where the light element, the light isotope abundances of deuterium relative to hydrogen, helium-4 and helium-3 and lithium-7 in old unburned stars, which, you can extrapolate to zero metallicity, was consistent with production calculations in the first few minutes of a Big Bang. At this point, people began to accept the Big Bang. It became generally accepted. So let me talk about what's needed to understand dark energy in terms of this cosmologically coupled black holes. What are needed is clean observational signatures. So let me give you a few. Black hole mass growth, if you can observe that, it's analogous to the cosmological redshift. Remember, we do have cosmological coupling of light. As the universe expands, the light stretches. How does the light know to stretch in its wavelength? It's coupled to the cosmology. So black hole mass growth is not the first thing that's cosmologically coupled, but that's one of the things that you could observe. You could also observe dark energy density tracking star formation, because stars make black holes. Black holes are the origin of these CCBHs. Anyway, that would produce an evolving dark energy density. And until recently, until a couple of years ago, we thought that the dark energy density was a cosmological constant. Anyway, the other possibility is seeing evidence of a conversion of matter, baryons, into dark energy. Because as matter falls into a black hole, it falls down, gets converted into this dark energy at the center, and then it grows with the expansion of the universe from the time of formation. That's the idea. So if you can observe any of these things, that's evidence, an observational signature of the CCBH idea. So CCBH leg number 1, black hole mass growth. In 2023, in February, we published 2 papers. One in Astrophysical Journal, which was just where we studied the growth of supermassive black holes in elliptical galaxies, not associated with cosmological coupling. And then we interpreted it in a companion paper in Astrophysical Journal Letters, which was observational evidence for cosmological coupling of black holes and its implications for an astrophysical source of dark energy. To say that this was controversial would be an understatement. This received a great deal of attention. The second paper, people don't usually read the data paper, but they did, 45,924 downloads of this. Typically, I'm lucky if I get about 200 downloads of my papers. This was this was unbelievable. And then the paper interpreting that as an astrophysical source of dark energy now has 126,000 downloads as of a couple days ago. And so this raised a huge amount of commotion in the community. And there were a lot of skeptics. I don't blame them. It's a new idea. It takes a lot of thinking, to understand it takes a lot of doing. Look how long it took me, 7 years. Well, 4 years. And so this is what we saw. So the the general relativity prediction is that if they have a species of compact objects that contribute a non-zero pressure to Einstein's equations, the individual masses will observationally grow. This is from Croker and Weiner, analogous to the cosmological photon redshift, as the A is the scale factor now, AI is the scale factor at the time of when this black hole first formed, and it goes to a power k, and so the mass will grow according to this equation. Okay, it grows as a power law in A. And what's interesting about the paper is that it says that that k value is related to the equation of state. It's -3 times the equation of state is the coupling strength. It's this number up here in the exponent. And so if you plug in p over rho c squared of -1, I know sometimes I use c equal 1, sometimes I don't. That's just what GR people do. Anyway, if you plug in -1 in here, you get k equal 3. So it should go as the third power of the scale factor. So it's special. It's motivated by non-singular black hole solutions. So if k equals 3, then the mass of the black holes will grow like a cubed, and then the number density will dilute of black holes will dilute with the universe after they're formed. And so the total energy density, which is the product of these two things, will be a constant. And conservation of stress energy and general relativity requires this. And if the density of black hole density is constant, the energy density is constant, then the pressure will be equal to these will be opposite each other, and the pressure in these cosmologically coupled black holes will be minus their density. And so therefore, black holes in aggregate will contribute as a dark energy species with an equation of state of -1 that keeps popping up. And the fact of the matter is, as proven by Croker and Weiner, the universe doesn't care if the dark energy is distributed throughout the universe or it's in blobs. In other words, they can come from black holes, which is contrary to what most people learn in general relativity. So what we did, and this was due to Duncan Farah, the first author on that paper, who came up with this idea. What he did is he took these surveys, WISE, SDSS, and Cosmos, and he chose only those galaxies, passively evolving elliptical galaxies, where you could measure the supermassive black hole at their center and the total matter, the total mass in stars. In other words, he picked a highly selected sample where there was no evidence for growth in the total mass in stars in the galaxies. In other words, there wasn't a lot of gas and dust left for anything to feed on. But we found there was substantial growth in the supermassive black hole at their center by following these type of objects over, and remember, it's a very selected sample. Other samples are messed up by accretion and mergers and all sorts of other stuff. These are passively evolving elliptical galaxies. Most of you have probably seen them. Anyway, so what we did is we took the redshift of each galaxy and we adjusted the value of k for each galaxy to line up the high and low redshift samples in the supermassive black hole mass and the stellar mass plane. So we did this individually for each galaxy. And we figured out what value of k was the best fit to make the two samples line up at high redshift and low redshift. And what you see here is that in the WISE and SDS sample, which are at lower redshift, and another WISE and SDS sample at intermediate redshift, and then the Cosmos sample, which is at higher redshift, what we find is that the coupling strength that makes the samples line up best is just about 3, which really was intriguing to us. We said, whoa, right? And so when you combine all this data and you get this best fit Gaussian there, what you find is the K value is 3.11 plus 1.20 minus 1.33. But the interesting thing is that if cosmological coupling does not exist, then K equals 0 over here is excluded at 99.98% confidence, which is greater than 3.9 sigma. Okay, that's pretty exciting, right? So we got excited and we wrote a paper on it, 2 papers, one for the growth of black holes. And what we found was that if you try to come up with a model using this cosmological coupling, in other words, stars make black holes. We know the star formation rate density as measured by various experiments. And then you calculate what fraction of them go into black holes. And there's uncertainties in this. And at that time, not a lot was known for the very high redshifts. But if you do that, you find that this range of green, this green region here, is the range over which we can come up with a model that would contribute omega lambda equal 0.68, which is the current value, of the dark energy fraction of the universe. And so anywhere within this range, and notice the data that we do have at high redshifts that is actually reliable, that came from the Hubble Space Telescope, and is completely independent of anything we measure with DESI or anything else, that this dotted line here, which is called Mato and Fragos, which is kind of like the most reliable values for the star formation rate density, lies right between the middle of that band. And so it's perfectly possible that black holes could indeed be the dark energy of the universe, that they could be formed where matter turns into dark energy. And then from that formation, the universe grows and stretches them and basically grows the mass through, again, negative pressure volume work done on the external universe by the internal stuff inside the black holes, and basically produces a greater mass than you started with, and because it comes from the negative pressure volume work. Anyway, that was the idea. And as you can imagine, there was a lot of controversy over that. And the way you resolve controversy is you do more measurements. I mean, that's what experimental physics is all about. So CCBH leg number 2, DESI had published its first year of data, and it was made public. And so some of the people that we started, you can remember some of the names, Duncan and Kevin and myself. We joined forces with some other people, Steve Allen and Brian Cartwright, Nico and Roger. Roger is one of the JWST leading investigators that has measured the star formation rate density. Steve is a fellow DESI member that helped build the focal plane with me, and I've known him since graduate school. And then Brian Cartwright is a very interesting character. He's after working with me for 6 years, he supervised my thesis experiment. After working with me for 6 years, he decided to quit physics. And I like to say that, but he tells me it's not because of me. But he went off to law school. He went to Harvard Law School, became president of the Harvard Law Review. And then he became Sandra O'Connor's first clerk on the Supreme Court. And then after he did that, he formed the 3rd largest law firm in the world and grew it to that, status. And then he became the chief counsel of the U.S. Securities and Exchange Commission. So he did very well as a lawyer. But then when he came to my retirement party, he met Kevin and Steve, and he says, I loved physics, but I couldn't see a future in it for me. He's a really smart guy, by the way. We said, well, why don't you join us on a physics project? And so this is what happened. So he's actually come back to cosmology, come back to astrophysics. Anyway, so, oops. So anyway, this appeared in the Journal of Cosmology and Astrophysics. It ranked #1 for outputs of similar age from that journal, and #3 for all of the outputs ever from the Journal of Cosmology and Astrophysics in terms of attention. And here's what we found: that the DESI-WOA parameterization tracks star formation. All the DESI year 1 WOA parameterizations show a dark energy density. If you just plug into that equation and the W naught and WA that you got from the different values for the different supernova data, what you find is that the dark energy density rose up, peaked, and fell down. So it rises from cosmic dawn around Z = 20. It rises to cosmic noon around Z = 1, and then it thaws as the redshift goes to 0. And this suggests that dark energy production is associated with star formation. Now remember, this thawing stuff over here is an artifact of WOA. It has to have a hump. Okay? It has to have a hump, and therefore it has to come down. And the idea is that stars produce black holes, and black holes produce these cosmologically coupled, well, the black holes are cosmologically coupled black holes, and then they grow with the as the universe expands. And this is what our model, using the latest values of the star formation rate density from this old Maddow curve, but also the new value that came from the James Webb Space Telescope data just this last year. And as you can see, the DESI DR1 WOA tracks star formation, which is the CCBH model, within 1 sigma. These are the 1 sigma bands. And so it's starting to get really interesting. Now, the plateau behavior is characteristic of CCBH with K = 3, because it will grow up to a certain value, black hole formation stops, and then, but thawing dark energy can be accommodated if you allow there to be some matter in with the, in with the dark energy in the center of these black holes, and that can be accommodated with K less than 3. So that you can do that, but we didn't see any reason to do that because the data is fine without adding that complication. So this is the DESI DR2 data for year 3, and it shows similar behavior, but much tighter bands. And if you plug in the CCBH model, the two models which kind of bracket the values that you get, they track within 1 sigma again, shows similar behavior. So that was leg number 2. Let's talk about leg number 3, matter conversion to dark energy. So what we decided to do is to form an external collaborator project with some of our colleagues, and also form it within the DESI collaboration as an external collaborator project. And so we got all sorts of good talent from DESI to join us. And just a month and a half ago, we published this article called Positive Neutrino Masses with DESI DR2 via Matter Conversion to Dark Energy. This paper was well within 0.5% of all of the outputs from physical review letters, of 99.95% percentile. It got a lot of attention. It was a DESI collaboration paper, and it went through thorough internal review before we sent it to PhysRev Letters. And it turned out to be not only an editor's suggestion, but also the cover article for Physical Review Letters. Some of you might remember that wonderful song on the cover of the Rolling Stone. Well, that's how I felt. So anyway, this is what we found, that another tension was resolved by using the CCBH model. What we found with DESI, for DESI DR2, BAO, and CMB, we could measure the sum of the neutrino masses because that's what's left over after you account for all of the mass in the universe. And remember, we're measuring the evolution of the mass density. And what happened is there was too much. It was, if you use the values from around the Planck time, it was just too much mass in the universe. And then the amount left over for neutrinos was too small. And if you allowed masses less than zero for the sum of the neutrino masses, it would peak at negative values, which is clearly unphysical. But even if you allow for masses, if you throw out the masses less than zero, the probability distribution kind of rises up and pushes against the sum of the masses being zero. And over here are the possible values for the neutrino mass, some of the neutrino mass from terrestrial experiments at accelerators. And it's in tension with those oscillation measurements because there's only a little bit of probability of overlap there. But W naught W relaxes the tension a little, as you can see over here. But what happens when you turn on CCBH, what you find is a nice positive neutrino mass that overlaps the regions that have been measured. And so it relaxes that tension in the sum of the neutrino masses that DESI was finding. And this Trinka star formation rate density can account for the baryon deficit of 30%. There is a missing baryons problem, which is about 30%. And, in the current universe versus what it was formed at Big Bang nucleosynthesis. And allowing for the dilution. And so both Trinka and Matter resolve this neutrino tension with oscillation measurements for both normal and inverted order. So anyway, that's what we're finding. The conclusion that you might reach from this is that black holes may be the dark energy of the universe. It could be right, it could be wrong, but the evidence is mounting. Cosmologically coupled black holes are a viable model for the origin of dark energy, and it survived 3 independent cosmological tests. It solves 2 major problems with all distributed dark energy models. The new cosmological constant problem, why is the dark energy density comparable to the matter density? Because it originates with baryonic matter, converted to dark energy in black hole formation, and then it grows through cosmological coupling to its current value. The coincidence problem, why now? Well, stars had to form to make black holes, and then the black holes had to grow with the expansion of the universe. That's why now. There are no other models that actually solve these 2 major problems. Anyway, CCBH is a fully physical model involving known objects, black holes, we've observed them, and known physics, general relativity. There's no modifications to general relativity involved. Independently measured star formation rates from JWST and Hubble. There are no additional cosmological parameters. It removes or reduces various tensions in the cosmological model. It accurately reproduces the measured cosmic expansion history. It explains the time-varying dark energy density observed by DESI. It eliminates the need for a phantom crossing as suggested by the DESI-WOA analysis. It explains the missing baryon problem. It resolves tension with neutrino masses as measured by terrestrial neutrino oscillation experiments. And it partially resolves the Hubble tension. So it also connects inflation in the very early universe with the accelerated expansion in the late universe. And it requires that we abandon our preconceived notion that dark energy is uniformly distributed throughout space and time. And it requires that we re-examine our preconceived notion of singular black holes with singular black holes with static horizons. If CCBH turns out to be correct, black holes in the future may become the laboratory in which quantum gravity and early universe physics can be studied.
Hello, darkness, my old friend. I've come to talk with you again.
So thank you. Are there any questions?
There was a question from the chat.
Well, let me look at the chat. Just a second. Would it be possible to observe a change in dark energy when black holes collide? We've been thinking about that. That is a very, very hard calculation to make, but they've done it. And we've started to think about what one of the problems is that in the Croker and Weiner formalism, we match the boundary conditions of infinity, but we do this by integrating Einstein's equations and using the Einstein-Hilbert action. And as a result, we can match the boundary conditions at infinity, and we can get to zeroth order that, dark energy, a dark energy solution for these black holes, with the, that they act as dark energy. But we need to we can only get the first order, second order, third order solutions through perturbation theory, because we've already integrated away. It's kind of like Gauss's law for gravity. It makes things simpler, but, it doesn't tell you what's going on, in detail. And so we don't have a detailed local solution right next to the black hole. And we also don't have an interior solution because we don't know the physics of what's going on inside. So it's incomplete as a theory. Hopefully we can figure out what's going on inside a black hole and what these first and second order. We've already, I can tell you that privately, we have calculated things out to first order. But in order to show that the first order calculation is correct, we have to do the second order calculation and show that it's small. That has not been done yet. You can watch for that in subsequent papers. But in order to understand what happens when black holes touch each other and start and merge, you got to understand the local solutions. And so it's hard.
So with this conversion of energy to dark energy, matter to dark energy through the black holes, does that still allow for global conservation of energy? Does that eliminate that from where the original idea behind the dark energy and dark energy is as the universe expanded, the total energy increases, right? Because
no, the total energy within a co-moving volume, in other words, one that expands with the universe, would stay the same. Because what's happening is the dark energy grows through negative pressure volume work on the external universe. When dark energy was spread throughout the universe, no one worried about that. They said, oh, okay, negative pressure volume work, you get more dark energy, that explains it. But now that the dark energy is in black holes, people are saying, wait a second, how does that work? Well, it's coupled to the external expansion. So the negative pressure volume work done by the matter inside the black hole on the external universe, since it's coupled, leads to increase.
They balance each other out, right? Yeah.
Yes. Yes.
Looks like Doug has asked a second question.
Check the chat again.
What about with neutron star mergers? Are the masses, densities too small? That is an incredibly interesting question. We have been worried about that because at the center of a neutron star, you have this, this nuclear equation of state, which is basically unknown. There are models that predict it, but it is possible that some fraction of the mass of a neutron star might be this, energized vacuum, and that it might coexist with the matter in the center. And then K would be less than 3. It might be less than 3 in a black hole if some matter is left over. And so we don't know the physics. And that's why when I said that black holes may become the laboratory in which to study this stuff, by studying what the value of K is, we learn about what's interior to this. And so if K is equal to 0, well, then this theory is kaput. But if K is less than 3, that might give us some indication that there's some mixture of matter and vacuum energy inside a black hole or inside a neutron star. And in that case, once we know the local metric for a neutron star, it might affect some of these measurements that can be made, where you have binary neutron stars, and you can observe that maybe. So believe me, it's on our radar. That's a very interesting question.
Was there one more question in the chat?
Yeah. Kurt Hillig asked a question on Zoom.
Look at the chat.
Oh, I see. What data would be needed to better refine the WOA model? Higher order terms. Measure. Oh, see, all of these models that we use to find these likelihood values in the DESI data, they extract the parameters of that model. CCBH is the first time we've actually applied a definite physical model that's associated with some physical object out there. not some parameterization. Now, people who write down these parameterizations will say, oh, they're physical. I don't see them as being physical in the same sense as CCBH because they're not objects that we can understand and study through independent means. But people have tried non-parametric fits to the DESI data. There's a paper that just came out recently. They conclude that dark energy density is changing in time. They agree with us. There have been, there's other parameterizations that can be used. People have tried polynomial approximations, but the problem is the data is not good enough yet to justify going to higher order terms without a model fit. Model fit, there's reason to believe that might be a good thing to do. But with the parameterization, going to a higher order term, you have to have more data. And so there will be more data. I mean, we have, we almost have 5 years almost of DESI data in the can, and we'll be releasing that at some point, probably next March. And then we have another 2.5 years of extension on DESI. And then starting in 1989, we're going to start DESI 2. It's already on DOE's books. And that's going to be another 7 years of data. And it's going to go deeper as well. And so there's also satellite flying. There's the Euclid satellite. So there should be more data on that. And there's also LSST that's just started up with the, Dark Energy Science Consortium that's going to look at that to try to figure out what dark energy is. So there's lots of experiments that are being done now. And there may be a lot more data in the future. And so there should be. And so, maybe it will survive, maybe it won't. And we'll see what happens.
Any other questions for Greg?
There, any intersection with the primordial black holes?
Oh, we thought about that. There's these, I'm not a big fan of, these microscopic primordial black holes because inflation basically prevents them from forming. So if you believe in inflation, it's hard to believe in primordial black holes. However, there's some physics that post-inflation could produce black holes, small ones. And if we find evidence for those in the universe, then that would form like a floor before stars start to form of black holes that would grow. But nothing's been seen yet. So.
And they evaporate rapidly, right? So
Yeah, well, they would evaporate, but that they evaporate because the surface area is analogous to entropy, and so the Hawking evaporation is a quantum gravity process, which has yet to be seen, and it may be connected with CCBH in some way, but CCBH is not a quantum gravity theory because it doesn't. But quantum gravity may be the reason why CCBHs can form in the first place. Because think about it, when you're forming a singularity at the center of a black hole, something's got to stop it. Well, what's going to stop it? What's going to stop it is some sort of quantum gravity process that results in some sort of vacuum energy that would hold back the collapse. Now, I've tried. This is an almost impossible problem in general relativity to model the collapse of a star. Oppenheimer tried it, okay? But he had a very, very oversimplified model, which has not been generally accepted. He basically used a Robertson-Walker interior metric, and he connected it with a Schwarzschild metric at the event horizon, the gravitational radius, and he obtained a oscillating solution. Okay, now of course he knew nothing about what would stop such a collapse at the time, but he obtained an oscillating solution that there was some sort of bounce at the singularity. There was a lot of criticism of this, but Weinberg in his book picked up on it and took it a little bit further and was intrigued by the whole idea. recently my colleagues and I have been playing around with Higgs dark energy. You know, there's the Higgs particle that's produced, that was measured, and it comes from the Higgs field, and we know a lot about that because it's been studied at accelerators. And one thing that we can tell for sure is that that the Higgs field in a collapsing universe inside a black hole, similar to what Oppenheimer did for that, which doesn't quite model what's really going on, that there would be a Higgs field that would be formed, and it would, if it doesn't stop the collapse, it would delay it. It would slow it down. There may be other scalar fields in the universe. For instance, the one that was responsible for inflation. But we don't know those fields. We do know the Higgs field. And the Higgs field, actually, we can show that it has a equation of state of -1. And so it would, it would contribute to the, slowing down of the collapse. But I suspect that some other scalar field, which, you have to know how quantum gravity works to make that work, might stop the ultimate collapse of to a singularity. And so my guess, if you want to know my guess, I'm just a simple experimentalist. Okay, I'm not a theorist. But one of the interesting things that's been put forward by theorists is that in the early universe, when you're creating magnetic fields and electric fields, that gravity, when it's so concentrated, would actually create magnetic fields in a what's called a hedgehog configuration, which, the field looks like a charge. And there are only two types of charges allowed in the universe. There's magnetic charge and electric charge. Magnetic charges have not been found. But one of the things that may happen is that in the early universe, just gravity turns into a hedgehog type of quantum defect. And that defect would naturally form magnetic charge at the Dirac charge of 137 over 2e, magnetic charge. And it would produce also electric charges. Now, the problem with the Dirac charge of 137 over 2 times the electric charge is that it is unstable. It would form a core of vacuum energy, which would then inflate it away, and we wouldn't see any monopoles today. Interesting, right? And so you would only see electric charge in the universe today. No monopoles. This was kind of like what Tufte talked about when he talked about what the magnetic charge, whether magnetic charges could exist. And so there were searches for monopoles, and they had, I was part of one, and they didn't find it. So, but all of this physics may come together in the early universe, and who knows what the origin of the universe is, and what the singularity is going to be, what the approach to a singularity is going to be like inside a black hole. One thing I know for sure is that a singularity is unphysical, so something has to stop it. And we just don't know the physics yet. Did I confuse you more?
Well, Greg, actually, it's good not to know all the answers, because that way they'll keep paying you to do research.
Well, no, I'm not getting paid to do research anymore. I'm retired.
Well, that's true. You're retired, yeah.
I can ask you what I think is probably a simple one that I just completely missed, but you were saying that the distribution of the dark energy didn't matter whether it was clumpy or whether it was broadly distributed in terms of what was measured or what was observed, right?
Yeah.
Like, because I mean, that's part of the theory of it has to be within the black holes.
Yeah,
Is there any observational data for it, or what are we making that?
no, it's based on a preconception of what dark energy has to be. They think it's associated with, it's some sort of quantum field fluctuations going on, and it has to be associated with the vacuum, which means all of space. And that doesn't work, it doesn't work by 120 orders of magnitude. And so why not imagine that black holes, trap vacuum energy and form the dark energy of the universe?
Okay, so we don't know of any kind of experiment.
No, it's kind of hard. I mean, if you start to study more things, somebody clever is going to come up with an idea. But the first step is you have to kind of say, okay, what if this theory is correct? What observational signatures would I see? And so look, we're a small group of people. As I say, they're ragtag. Okay, boy, are they ragtag. Anyway, what I hope is that people see these few observational signatures and then start coming up with ideas of their own and studying it. So far that hasn't happened. It's always been Kevin and I and Duncan and a few others. And I'm hoping that, theorists start to take note, after these 3 legs have been shown to support it, and start working on this problem. I would love for theorists to start working on the interior solution. I would love that. But, look, and with no disrespect to the theorists, while us experimentalists have been building experiments like DES and DESI and getting lots of data, for the last 25 years or more, the theorists have been sitting around, patting each other on the back, telling each other how smart they are, saying words like Einstein a lot, and basically sitting on their butts, not doing anything. They haven't come up with anything. And so why is it necessary for this funny little group, that formed to come up with these ideas? These are ideas that should have been explored by the best theorists in this nation and in the world. And I'm a little annoyed at them that they've been spending the last 25 years and nothing has come of it.
More like 40. Yeah.
What?
Never mind.
86, right? From 86 till now?
Yeah, it's more like 40 years, I thought.
Oh, no. It's the idea of non-singular black holes has been around for, and having energized vacuum in them has been around for, since Gleiner. Oh, by the way, if any of you want to read a story of deprivation and hardship of a physicist, go read the story of Ernst Gleiner. It's incredibly interesting. This guy suffered so much in his life. It's just astounding.
Any other questions for Greg? Don't say anything on Zoom, nobody in the room saying anything. So how about a big thank you?
Well, thank you. It's great to talk to you. We'll do this again sometime.
Pardon me?
We can do this again sometime.
That'd be great.
Excellent. Yeah, I always like to go for speakers, see if they want to return, so have you volunteer like that, you just make my job easy.
Yeah, so in a couple of years,
remember that.
contact me, ask me if something new has come up, and I'll tell you.
Excellent, you can put you down for
And so, the West Hawaiian Astronomy Club asked me to give a talk, and so I'm going to recycle this talk into the West Hawaii Astronomy Talk.
Okay, all right.
Thank you.
You saw you're still in Hawaii right now. Like,
This has been fun.
can you move that over to the room? Yeah, I'd like to look out that window.
Yeah, I'm sure it's
Yeah.
a beach.
The sun's still shining over there.
Okay, so I'll leave you now. Okay, bye.
Bye. Thank you.
Appreciate it. So Greg has decided he wants a T-shirt for a little gift for our guest speaker. But I was thinking I could entertain a motion to have the club president deliver that. Something tells me the IRS would consider that private benefit and there would be a problem with it. Those are tax exempt, but I'd still get Hawaii.
If you need some help, you might get lost.
Okay.
Only if I get to come along and make sure you give it to me.
Yeah,
We are
technically we have the money.
have to go.
Okay.
We saw Desi when he was a kid.
Really?
In 2018, I brought my son out to work and we saw them putting this together. I didn't know what it was at the time, so. I mean, it was just a few, we got there on the night, the day, and the docent, there wasn't anybody up there. So he said, yeah, well, just the three of us, my son and him and myself. Yeah, we'll go right up, we went right on the floor. It was really cool, it was awesome.
Yeah, I imagine if you didn't know what that was, you'd probably have looked up.
Well, I mean, yeah, it was just, he tried starting explaining it, of course, it just went.
No, it's only 600,000 parts.
Yeah, really.
Okay, for reports, I have a few things here. Probably the first and most significant one is you remember at last meeting, I was still looking for a webmaster and another vice president, and we have found both of them. So with that, I don't see Barry in the room, do I? No, it's afraid I wouldn't recognize him. Anyway, we have had Barry Chapman volunteer to be our new webmaster, and Tim Miller, who is here to be our newest vice president. Both of them would be working on our website. Now, Tim might get involved in other things too, being a VP, but that would be one of his main things. The idea is he'd be working like on the front end of the website, that kind of stuff. And Barry, since he has, his stuff is more into kind of the engine of the thing, would be working more on the back end of it. But between the two, I think we got a good thing going here. So in fact, Greg has already called for a meeting with him and me and both of them.
Do we need to vote
over this?
We do. Accept this. I make a motion to.
Are you making a motion?
I am making the motion that we vote on Barry Chapman being webmaster and Tim Miller being VP.
Do I hear support?
Or.
All in favor?
Aye.
Anybody opposed? Okay. Congratulations.
Yeah.
Sure. Excellent, thank you, Cameron. Yeah. Okay. So as you may have noticed, if you saw your email earlier, I've gone ahead and canceled the open house for tomorrow night. I think the forecast is adequately bad enough that I could risk doing that. I did inform the people from the school in Dexter, Wayne Classical Academy. And in fact, he emailed me back while I was sitting here that he did get the message and they are planning to attend next Saturday. Right now, the forecast looks good for next Saturday, but you know how it is in Michigan. If it looks good now, that's actually a bad thing. Because it's probably wrong and the opposite of good is anyway, but we'll see what happens. They might be right. Also, we are working on an event for Chelsea Elementary Parent Teachers Organization, PTO. And that is set for January 30th. It's out at some education center in Chelsea. I'll send more details on. We got a little ways to go yet. But I'll be looking for some help for that. That's the Chelsea Elementary PTO. Yeah, Jeff and I are planning to attend, but we can always use more. I did get an email. I got a response. I asked him about a table, that kind of thing, and he basically said, just tell us what you need and we'll do it.
What was the date again?
Pardon?
What was the date of the event?
30th, January 30th. We've also been contacted by the Belleville Library about doing an event for them, as she said, in late winter, early spring. So that's just the beginning part of the discussion. It actually came through the Night Sky Network, and it was instant in her email. She was really hoping that she'd hear from us because she's put out several inquiries and gotten no response from any other astronomy clubs.
There was an email about.
No.
I know,
Well,
You'd have to look up the.
because I live in Melbourne.
Well, I can find out and let you know.
All right, yeah, just let me know.
We need to get you added into the officers email list. There's a group for officers.
Okay.
Yeah, yeah.
You have my email. Obviously.
Yeah. Let's see. Oh, and also, I kind of went a little crazy with guest speakers.
Yes, you did.
I get our that out once in a while. But what happened is I had already finally shored up the one and only David Levy for our December meeting. So that is for sure. Now that of course will be a Zoom meeting too, being he's in Arizona. But that should be exciting. And then when I was at Astronomy at the Beach, I just happened to run into Ken Burke. Some of you may remember him. He has actually spoken to us several times. And before I even got thinking about that, it's been a while before he talked, he said something. So he's got something, I forget what it was now. Something pretty interesting, something about another famous astronomer or something. He hasn't quite put it together, but he'll have it like in spring, summer, somewhere there. So he said contact and we'll arrange a date on it. Also, before Brother Guy's first keynote talk at AATV, I was up the front there talking for a little bit. And I happened to mention to him, and I was thinking about seeing about another appearance of him, because as you know, he's kind of a regular guest speaker for us. And I said, but I see Astronomy at the Beach got you first, and for 2 nights, so I'm not gonna bother or anything. And I happened to mention it was really cool. We got the news that Father Richard D'Souza had become his other half, so to speak. And so he goes, hey, you should get him to be a speaker for you. And I said, well, actually, when he was here at the U of M, we did have him do a talk for us. It was really good. And he goes, he'd do it again. So hint there, let's go after Richard D'Souza again.
Is he retiring as
No,
the director?
no, what happened is Brother Guy was the director of the Vatican Observatory Foundation, but also the observatory. So what they've decided is that this was really a lot of work for somebody to do, especially when that person's traveling all over the world all the time. So, and I don't know if this was Pope Leo's idea, was cool, but they decided it was too much, that they should split that and it should be 2 people. So Brother Guy will continue to be the head of the foundation, and Richard D'Souza is going to take over the observatory. So actually, Richard D'Souza will be doing more of the science stuff now than.
I'd rather have the observatory.
Oh, absolutely, yeah. Yeah, well, that's what he said something about. He goes, yeah, he's gonna be doing the fun stuff now, so.
You know, the brother guy's no slouch either, so.
Exactly.
Yeah, either of them are good speakers.
Oh, yeah, both nights he totally filled that tent, so.
Yeah.
Yeah. Oh, and if that's not enough, we got 2 more. Sebastian, that was our speaker last month. Of course, we had those difficulties, but got over it. Is also mentioned, in fact, I think he might have mentioned it during that talk, that he is doing a major upgrade of the software, and if we'd like, he'd be more than happy to do another talk to go over what that upgrade is and.
A little one.
Yeah, and do that. He feels kind of bad that it didn't go well that first time. He felt like he had to push things along a little too quickly. So he's hoping less chaos and he can go with this update, so that would be coming up. He hasn't got this update yet, but that's coming up soon. And if that's not enough, Jeff Kamanis and I have been talking about doing another C-Star presentation. This would be kind of an advanced version that's sort of based on things that we've learned based on our real experience with them. On the other hand, we did question a little bit, are we being kind of redundant, because there's a lot of stuff on email flying around about C-Stars. What's your opinion? Would that be something that would be of interest to people, or? Okay, saying that now, nobody's throwing anything at me. So, okay.
Plus, since the talks are all archived,
Oh, that's
you don't have
true.
to try and hunt through
Yeah,
emails.
right, that's a good point. Good point. And actually Jeff gave me a little outline today earlier that some of the stuff he's learned, it was really good stuff, so. I got a feeling he'll be doing more of it than me. Okay, then we'll proceed with that, probably there, we just filled up all of the next year.
It's not quite. It's close.
Pretty close, so. But hey, I like to be ahead of the sticks, you know. And I think at last, that's all I have. So I would like to see if our new Vice President, Tim Miller, has anything.
Okay, impromptu, sure. So Barry and I talked a little bit about just kind of what we were thinking of doing, and a lot of it would be starting off just figuring out where the web, the web presence is at this point in time. And Jeff and Barry and I are gonna be, you're gonna be in that meeting too. We're starting about a couple weeks. We're just trying to get a baseline about where we are, and then look at what we need. And then some kind of report going out to the club about, what we think, where we are, and then figuring out where we want to go with it. What we want, how we want that website to look, what we want it pretty much more would be the function. And how it would benefit us and the people who would be, looking to us for information. And then, Barry's gonna work on putting it together in a point where it's easily editable, and then we can maintain it better, so we can be updated easier and kept current. And that's kind of some of the things I noticed about it. There were some things on it that just looked like it wasn't current, because it's hard to do all that and find ways. His specialty, what he said is, he's making interfaces to get the information in and creating the structure underneath. So we figured, as what Charlie said, he's gonna focus on that part of it, because I know enough to be dangerous. And that's about it for that. And then I will focus on the communication between us and then Barry to get the information into it, if that makes sense.
Does, yeah. No,
That's
we'll report back to you what we think and everything, see if club's opinion is.
right.
Maybe you'll tell us we're full of crap. Doubt it, but you never know. So. Okay. How about Don Foley?
Hey, Ken. I got my report written out.
Oh, thank you.
So. The Observatory Committee, Jack Gisbin, Jake Forrester, and Bradley Dugnell, me and Tom Arnold, we met out at Peach Mountain on Sunday, October 5th, to address the issues that Jack had. So it's and the battery charger for the mirror box, which operates the mirror fans, was thought to be defective. So I bought a new charger. And I put the connector in, so that's ready to go. And then we can hook the charger up and check out the batteries. Sky, we executed that the Sky Commander's 2-star alignment worked, the servo had functioned properly, and connections to the Sky Safari worked. However, the Sky Safari disconnected to the meeting from Jack's phone, which was kind of neutral. And the Lowbrow 17 network didn't appear anymore, wasn't available. So we needed to do a power reset of the Sky 5.3 to get the Lowbrow network back. And then we were able to reconnect it. So maybe something there going on with Sky 5.3. So I updated the manual to include a troubleshooting section to provide directions on what to do. You have Sky Safari disconnect.
That's called you.
Right. I opened Beach Mountain for the members Wednesday night. Nathan Murphy came up and joined me. And he saw that the binocular and cold radio station have been rising. I had a good time with it. That's one. I had. I know how hard it is to take notes, so I wrote. Appreciate it.
Thank you very much. And
I just sent out an email to the officers asking to add Tom and Barry to our officers email list, so we'll get that moving. My wife has updated the Ann Arbor Observer with the November meetings and events. So that's taking place. I had another speaker lined up, but I haven't actually been able to contact them yet. But he's a past speaker and has written a new book. And so it's something about the cosmos. So he's looking at James Webb and what the output from that is and interpreting it. And so we'll have, that's one more possible speaker that I've got. As a lead.
Is that Ethan Siegel?
Yes, it is.
Oh,
That's the name. So
Yeah.
I couldn't remember the name off the top of my head, but same guy. And he's got, I have his old book, which is on the James Webb. He's got a brand new one that's coming out.
He's got a webpage where you can put in a request.
Okay,
Are you familiar with the webpage?
nope. But I'll go do that.
I'll send you that link.
That'd be great. Thank you. And that's all I've got.
Okay, thank you, Ken. Jack.
Just a couple things, we've once talked about the, Lowbrow flyer. There was a copy of it in Young Astronomer, and I took that out because they wanted to make some updates. And I found a way to break it down.
You wanna show that on here or not?
Pardon?
You wanna show that on here? or-
You can show it on the.
Okay, do that.
Oh, Seth, let's see what happens.
Here's the, yeah.
I was gonna do that wide format.
Okay.
I think I gotta get back here. Hello.
I'm not sure we can.
Oh, there.
It's coming. There we go.
Okay. Now,
Actually, we can probably.
now, just to give you a little idea of what's going on.
Good.
They wanted to start republishing the flyer. And we were looking for an old copy, but anyway, I used my copy, downloaded into the PDF. And it converted to DOCX, to edit enabling and all that kind of stuff. And the whole thing came apart, which allowed me to go in and go right to Detroit Observatory. And I just made these changes to see that it did work. So we want to go back and redo the flyer. We should be able to do that. I don't know who wants to take that on reissue because they want to type up and make some changes to it too, because this particular one that was an old one on the Young Astronomer website. So we'll probably ask to find somebody that will be interested in.
Want to forward that to the officers, Liz? Or forward the doc X to the officers?
Yeah, I can do,
And
yeah.
that way, if we find the, willing victim, we can.
Yeah, that's fine. Leave that on here.
Before we have to draft.
It's off the bit.
Finally, the other project we were working on, something that Don Foley was talking about, moving the 17.5 inch telescope sometimes gets to be a problem. And
In and out of the observatory.
yeah, in and out of the observatory because of the weight and the movement and everything. So we're just looking at a few things with front of the observatory, some of you would know, and maybe taking this area down here in some kind of metal board pathway, create some kind of little sidewalk. So we can roll the 17.5 inch up here a lot easier, make it a lot easier.
As you pointed out, it slopes away and to one side.
Yeah, yeah.
So it's kind of like this, you'd be listing as you come out of there.
You would look like this, it's another part. Yes, you're
Yeah.
right, 'cause you see all the cars there?
Yeah.
It goes all the way down here.
It gets lower on the right side than on the left side as you walk.
It doesn't feel right when you're going up there, even for me, it doesn't feel right.
It's still, until you get to the concrete.
So, yeah, we're looking at something we can work across there and then just make it easier. You can only go so far out because there's a driveway here where other cars do come down, unloading things and that. And the idea is that it's something that we can easily maintain and take care of.
Possibly movable, probably not permanent.
You know, even if it was movable, November, December, you could put it in the observatory.
Yeah.
And then take it back out March, April or something like that. depending on how complex it gets to be to build it. So those are just things we're looking at in the observatory. I guess the next thing is getting ready for October the 25th.
Right.
Out there, it's
I'm
hopefully.
greater.
Oh, you're okay. I plan on coming out there. Anything else? Other
We
than that,
we don't have a,
Coordinate.
on October 25th, you'll coordinate.
I'll coordinate it.
All right.
Thank you.
oh, okay.
So you'll coordinate, I'll be greater, he's running the math, we just need to scope it.
But
Well, that's.
I don't think we need many scopes because I don't think we're gonna do our top.
But a couple.
If you're looking for it,
Yes, thank you very much.
This is the one I was actually.
Maybe it was still on, it's looking at the table. And Charlie, you can switch the video back.
Oops, yeah. Sorry about that.
No problem.
Yeah, it'll be later on the talk. Be going
Do
over.
we got anything else?
No, anybody got anything else?
Jordan.
Motion to adjourn?
Sure.
Anybody?
Sorry, I gotta catch the ball.
Anybody opposed?
Thanks so much for having me.
Well, that means that we're all adjourned except for you. All right, thank you very much.
if we have